Hello everyone. In this collection of lessons, we begin to study what's called systems of equations, finding where graphically two graphs cross. They can be lines, they can be other types of functions as well. And then also looking at tools to solving those systems algebraically. To start and kind of refresh your memory about what all that entailed, we're going to try a question on the whiteboard. So pull out your whiteboard, and what I'd like you to do is to graph these two lines and find where the two lines cross. And once you have your what we call the point of intersection, check that that is actually where the two lines cross algebraically. If you know what that means, go ahead and do so. If you don't, then you're going to have to wait until the video becomes unpaused and I can go through that with you. But let's maybe pause the video for a minute and a half now so that you have a chance to try this. So pause the video for a minute and a half, try graphing these two lines and finding where they cross. Okay, here we go. Hopefully you had a chance to try. Let's do this one first. I'll use red. You would start at 4 is the y-intercept, and then the slope is -2/3, so the rise is down 2 and the run is right 3. Remember, the top part of the slope is the rise up and down, and the bottom part of the slope is the run. If it's negative, only one of the items is negative. You can't have both because that would make a positive. So if it's a negative, most of the time we think about it as just the top part is a negative. So down 2 and right, 1, 2, 3. Down 1, 2 and right, 1, 2, 3. And then you could get the other parts by going up 2 and left 3 would be the same as well. And there's my first line. I would have sketched it in. Second one, maybe I'll do in blue. This one's a little tougher to graph. You can use intercepts if you like, or if you solve for y, you would subtract the 2x and then divide everything by a negative. You get a -4 plus 2x. So this one starts at -4 and goes up 2, right 1, up 2, right 1, up 2, right 1, until you find the intersection. And we see that it crosses at the point 3, 2, which means if I put 3 in for x and 2 in for y, it should make two true statements. So let's check. -2/3 times 3 plus 4. That leaves us at plus 4 is 2, and that's exactly what it needed to be. The other one, if I put 3 in for x and 2 in for y, I get 2 times 3 is 6, 6 minus 2 is 4, and it works for that one as well. So it works for both. That's what we mean to check it algebraically. So our goal for this chapter is to solve systems. What we mean is find where two graphs cross. That point of intersection needs to make both equations true because it's the only point that's on both lines. If you have your note packet out now to the very first section, you'll see that the section that we're talking about today says something about solving systems with substitution and elimination. We're actually doing what Algebra 1 and Algebra 2 would do in about a chapter. So this is definitely a review day, but we're doing it in a day as opposed to an entire chapter. So this section concerns itself with techniques for finding where two lines cross. As we will see, businesses call this the break-even point. Prior, we just did this by graphing. So the very first tool in our toolbox would be graphing. However, if you graph the following equations, these two shown, you'll see, if I zoom in, that the solution is not at an intersection. So is that like 7? It looks like maybe just a little past. 7, -2.2, like we don't know. So graphing's not always a great choice because the problem is what to do if the intersection is not integers, right? So how do you estimate if there's decimals or fractions? We need better tools. So graphing's our first tool, but we're going to need better tools. So the next tool that we would have is something called substitution. The steps for substitution are already in your note packet. You can read them right now. Step 1 is to solve one of the equations for one of the variables. Step 2 is to substitute that variable into the other equation and solve. Step 3 then is to substitute the value you got in step 2 into either of the original equations and solve for the other variable. I know you've seen this before because it's covered in Algebra 1 and in Algebra 2, so we're doing this mostly as a review because the ones that we will do that are more new to you later in later sections will be much more algebraically intensive. So here's how the idea works. We know from the first equation that y is equal to 1/2 x minus 6. So when I'm reading this second equation, I have 2x plus 4y equals 5. I might not want to try to solve this by graphing because, as we just saw, what if it doesn't cross at a nice intersection? So what we're going to do instead is we're going to solve this algebraically using the tool called substitution. So when I read this bottom equation, 2x plus 4y equals 5, I can't solve for x or y because they're both in the equation. I need to rewrite this equation so that there's just x's or just y's in there, and I'm going to do that by using this clue up top. Instead of writing 2x plus 4y equals 5, I know that y is equal to 1/2 x minus 6, so I'm going to rewrite y as that, because that's what y is actually equal to. So this second equation becomes 2x plus 4, and instead of y is equal to, what it's equivalent. It's equivalent to 1/2 x minus 6. So I only have one type of variable to work with, and I can solve. I'm going to do the first step of distributing. So then I get 2x plus 4 times 1/2 is 2. 4 times minus 6 is minus 24 equals 5. Add the 24 over the other side, and I combine these two x's. I get 4x. 24 plus 5 is equal to 29. 4x divided by 4, that's going to be, what, 7 1/4, so 7.25. So there's my x coordinate. These two lines would cross at 7.25, comma. Now how do I get the y coordinate? I get the y coordinate by taking the x value, and I can either plug it into the first x or the second x and solve for y. I think the first one might be easier because y is already solved for. So I get y is equal to 1/2 times 7.25 minus 6. Here's where you would probably appreciate having a calculator. Otherwise, it might be a little tough to do a 1/2 times 7.25 in your head. So 0.5 times 7.25 is going to give us 3.625 minus 6. I get a y coordinate of negative 2.375. So negative 2.375. And that is where those two lines should cross. That tool that we just covered is called substitution. It's called substitution because I'm substituting the value of one variable to rewrite the other equation so I can solve for one variable at a time, because you can't solve for two variables with just one equation. We're going to try another where you actually have to do a first step. So if I look at this one, our goal again is to solve by substitution. You already have the steps in your note packet if you'd like to read along. Our goal is to substitute. The difference here, though, is unlike the first one we did, the first one already had one variable solved for. So you need to look and think what variable would be the easiest to solve for, and there's probably two. Actually, maybe, yeah, probably two. This x would be fairly easy to solve for because I'd add the y over the other side, or this bottom x wouldn't be too bad to solve for. I would just subtract the 4y. Let's do the top x. If I solve the top x to get x by itself and add the y over the other side, I get that x is equal to 2 plus y. Now I'm going to take that x value and substitute it into the bottom equation. There's no number out front, or if you want to, you can think about it as being a 1. So if you distribute a 1 through, it's not going to change it. So when I substitute down here, I'm going to get 2 plus y, and then I have the plus 4y equals 17. I can combine this y and that 4y to get 2 plus 5y equals 17. If I subtract the 2, I get 5y equals 15, and then y equals 3. So I have half of the point of intersection. I know that those two lines are going to cross at blank, comma 3, because I know the y coordinate is 3. Now to get the x coordinate, I put 3 in for y in either the first or the second equation, or I can even do the modified first equation. I'm going to do the modified one because x is already solved for. So if I put 3 in for y right there, I'm then going to get x is equal to 2 plus 3, and that is 5. So these two lines should cross at 5, comma 3, and I just want to show you the picture of it. You'll notice that they do. They cross at 5, 3. That is the tool of what we would call substitution. Sometimes, though, substitution can be unnecessarily difficult. Like if I had this one right here, you'll see none of the 4 variables, top x, top y, bottom x, bottom y, are very easy to solve for. Like if I solve for the top x, if I subtract 2y and then divide everything by 3, and then I take this value and I substitute it in for x in the bottom equation, I did it right here, you'll see like nothing's really going to come out nice here. I'm working with fractions. It will work. You just have a lot to keep track of. You'll have to use decimals or fractions and keep track of them. So although substitution, it will always work, there are instances when it would be better to utilize a tool known as elimination. And you studied this in Algebra 1 and Algebra 2. The steps for elimination, I already have in your note packet. They're right here. Step 1 is to get either your x's or y's matched up so we can eliminate them in step 2. Sometimes you might need to multiply one or maybe even both of the equations to get the coefficients. The coefficients are the numbers in front of your variables. So the coefficients back here were 3, 2, 9, and -8. You might need to do some manipulation in order to get those coefficients to match up. That means to be the same number. Either positive or negative is not important. That'll just affect step 2. Step 2, then you're either going to add or subtract the equations to eliminate one of the variables. Step 3 then is to solve for the value of the variable that survived, the elimination. And then step 4 is the same step that was the last step in substitution. Use the value that you found in the prior step to solve for the value of your second variable. So let's try it. If I look here, I could get rid of the x's if the top one was 3 times larger, or if the if the top one was 3 times larger, I could get rid of the x's. I could get rid of the y's if the top was 4 times larger. It does not matter. We just would need to choose. Let's do the y's. If you want to try to do the x's, you can do that on your own, and then we should be able to match at the end. So if I multiply the top equation by 4, if I do the left, I also need to do the right side to keep the equation balanced. I'll then get 12x plus 8y equals, and then 48 times 4 is going to give us 192. The bottom equation just stays the same because now that y's will be matched up. It's 9x minus 8y equals -24. Now I either need to add or subtract to get the y's by themselves. Or sorry, to get the y's eliminated and the x's by themselves. If you try subtraction, watch what will happen. 12x minus 9x, you're just subtracting like terms. We'll talk about in the next slide why this works. But 12x minus 9x is 3x's. 8y minus -8y's, that makes 16y's. That doesn't get rid of them. So you should be adding here. You end up, it turns out you add if the signs are different and subtract if the signs are the same. So add if the signs are different, and you'll see that we subtract if the signs are the same. The signs being positive or negative. Sames. No, just same. Same. So we're going to add. Once I do that, 12x plus 9x, that's 3x's. 8y plus -8y, those get eliminated. That's what step 2 is. 192 plus -24 turns out to be 168. If I divide that by 3 to get x, I get that x is 56. So I'm halfway there. I know that these two lines are going to cross when x is 56. To get the y coordinate, I put 56 either in for x in the top equation or the bottom. It doesn't matter. Let's do the bottom. 9 times 56 minus 8y equals -24. 9 times 56 is going to be 504 minus 8y equals -24. Subtract 504 from each side. I then get -8y, -24 minus 504. You might need to use a calculator and make sure you're keeping track of your signs. You get -528. Divide by a -8, and you'll get that the y coordinate is 66. So these two lines should cross when x is 56 and y is 66. You could check by putting that point in for x, so 56 in for x, 66 in for y, and the equations, and they should work out. Something's not right here. I can already see 56 going in here is not going to make 48. There's a sign error. Where is it? 9x, multiply the top by 4. That looks fine. The bottom stayed the same. If I add, that looks right. Put 56 in here. Subtract. I am not seeing it. I want to say Let's check it real quick. So I can tell because if I put 56 in for x in the top equation, 3 times 56 plus 2 times 66, that is not going to equal 48. So I'm trying to find where the error is. If you multiply the top by 4, that'll make 12x, 8y, and 48 times 4 is 192. The bottom equation is the same. Add the two equations. That looks right. You put 56 then in. 9 times 56, 504. Subtract. Negative 24 minus 504, 520. That's interesting. That should have been no, that's negative 528. Yep, negative 24 minus 504. Yeah, that's negative 528. And then divide by a negative 8. I'm getting 66. Why is it not checking out? Let's see here. Let's actually use Desmos to graph and see what we should be getting here. I'm not seeing the error. So give me a second. Just pulling Desmos up. Two equations, 3x plus 2y equals 48. It's a good example, though, of checking your work and using technology to do so. So I need to zoom this out. Yeah, 812. So something really went off here. Where is it? Oh, it was right back here. 12 plus 9. Yep, I wish that I'd been present. So we need to go back and fix that. Yeah, these numbers are too big. But there you go. That's why you check your work. 12 plus 9, 21. There we go. So, sorry, you're going to have to use your eraser if you were just following along without thinking. 12 plus 9 is 21. X is 192 minus 24 is 168. Now, if you take 168 and divide by 21, hey, there's our 8. That's much better. If I put 8 in, if you do the top or the bottom, let's do the bottom again. It should work out this time. We don't know the y coordinate. 9 times 8 is 72, minus 8y equals negative 24. Subtract 72, negative 24 minus 72, negative 96. Divide by negative 8, and there's the 12 that we saw. So these two lines cross at 812. And they did when we checked Desmos. So there's an example of solving using elimination. Just a little aside of why this works. So let's say I had these two equations and I was going to solve via elimination. You would notice that when I line these up, my cancel out. So this is the reason why elimination works. Let's say I want to add 6 to this side because that's what I'm going to do. I have the 4 plus the 6. So if I add 6 to the right side of the equation, you've always been told when solving algebraically ever since maybe middle school when you first started, what you do to one side of an equation, you have to do to the other side. So I've added 6 to the right side. They would say, okay, you need to add 6 to the left side. The benefit on the right side is 4 plus 6 makes 10. Those are like terms that we'll add together. Over here, though, the 6 can't communicate with the y or the x. So there's really, it's not helpful to add 6 on the left side. So I need to add something that has the same value as 6, but is going to be more useful and can communicate with the x and the y, and that's where I use the hint over here. 6 is equal to 2x plus, or 2x minus y. So instead of writing plus 6 over here, we're going to write that we're adding 2x minus 6. Or it's not 2x minus 6, 2x minus y, because that is the same value as 6, but it will allow us to communicate over here and then do y plus negative y, and then the 3x plus 2x and make the 5x's, and then go solving. So you are adding the same thing to each side. That's why elimination works. It's just they don't look like they're the same value because one's written with variables and one is written with numbers. Okay, now we're going to do an example of elimination where you actually need to change both equations. Like I can easily get from 3 to 5 or 4 to 6 without using decimals. So I'm going to get them matched up using the idea that I'm going to multiply both of them. So for example, if I wanted to get the x's matched up, I would probably try to get them both to be 15, multiply the top by 5 and the bottom by 3. If I want to get the y's matched up, some people would say 24, multiply the top by 6 and the bottom by 4, or you could do 12, it'd be a smaller number, multiply the top by 3 and the bottom by a 2. I'm going to do the y's because this will be an example of when the signs are the same and we're going to need to subtract. But if you want to do the x's and get them to be 15, I think that is probably the better choice. But I just want to show an example of what to do when the signs are the same and you need to subtract. So I'm going to multiply this whole top equation by 3 because I'm trying to get the y's to both be 12. I'll then get negative 9x minus 12y equals 27 times 3 is going to be 81. Bottom equation, multiply it by 2. I then get 10x minus 12y equals negative 14. Now I need to get rid of the y's. If you tried adding negative 12y plus negative 12y does not get rid of the y's. That makes negative 24y's. That is why if the signs are the same, you need to subtract. Negative 9 minus 10x, that's negative 19x's. Negative 12y minus negative 12y, that's going to make 0y's. 81 minus negative 14. I'm even going to write that. 81 minus negative 14. You got to subtract all like terms, like decimal places back in elementary school. That's going to make 95. Divide by a negative 19, and you get the x-coordinate is negative 5. Once you have the x-coordinate, to get the y-coordinate, you put negative 5 in for x. You could either do the original whole top equation, the original whole bottom equation. You could do the new bottom or the new top. It doesn't matter. I'm going to do the... Let's do the original top. So then I would have negative 3 times negative 5, because that's what x is, minus 4y equals 27. Negative 3 times negative 5 is 15, minus 4y equals 27. Subtract 15, I get negative 4y, and that's 27 minus 15 is 12. Divide by a negative 4, and you get negative 3. So those two lines should be crossing at negative 5, negative 3. This section really assumes that you're solid with your algebra skills of doing some quick addition, subtraction, and multiplication. So you might need to refresh. That's it. Using elimination when you need to change both equations. And I'm going to ask you to try just one today on the whiteboards for the yo-yo. So you can solve this system by either doing substitution or elimination. One tool is going to be much easier than the other, but you choose it for you. So pause the video now for maybe 2 minutes, unpause it once everyone has had a chance to try. So please pause the video now, come back after 2 minutes. Okay, the answer you should have got is 4, negative 1. Probably best to do elimination. If you do elimination, let's say you get the x's matched up, I'll just show what the first step would be. If you got the x's matched up, you don't need to multiply the top equation by anything, because you just need to multiply the bottom by 3. So the top equation stays the same of 6x plus 5y equals 19. The bottom equation you multiply by 3 though to get the x's matched up. 6x plus 6y, or sorry, 9y, 6x plus 9y equals 15, and then go subtract. 4, and voila, there's the y coordinate, and then you could find the x. So there you go. Last little parts we're going to talk about is unique systems and then one application. So we'll do 2 unique system situations. So let's say this is an example of using substitution. Why is it substitution? Because y is already solved for. So I'm going to take 3x minus 2 and I'm going to substitute in for y in the top equation. I then get 15x minus 5 times 3x minus 2 equals 10. Then I go solving. Distribute your 5 through the negative, and I get minus 15x and plus 10 equals 10. And you'll notice, hey, 15x minus 15x, these cancel. That means it's 10 equals 10. That means the values of the variables went away, and we get a true statement, which means it doesn't matter what value you pick, every value would work. So this is actually an example of an infinite solution. It means that those two lines are actually the exact same. If you solve for y in the top equation, you would see it's the exact same as the bottom equation. Let's go ahead and do that. 15x minus 5y equals 10. If you solve for y by subtracting 15x, and then you get 10 minus 15x, and then divide by a negative 5, you'll get negative 2 plus 3x. And that's the exact same as what we had right here, which means those lines are actually the exact same. They are always crossing. That's why we say there are infinite solutions. Second special case one. This is an example of using elimination. If I want to get the x's to match up, I would take the top equation and multiply it by 2, and I'm going to write it right below. So 2 times 2 is 4x, 2 times 3 is positive 6y's, 2 times 8 is 16. Now the x's are matched up and they're the same sign, so I'm going to subtract. 4x minus 4x is 0. 6y minus 6y is 0, and so I get 0 equals 12 minus 16 is negative 4. This right here is a false statement. So not true, which means that there must be no solution. If I actually graph those two lines, I would find that they are parallel. If you solve for y, so I'll do that kind of in my head. If you solve for y in the top one by subtracting 2 and then dividing by 3, the top equation would become y equals 8 thirds plus 2 thirds x. The bottom equation, if you solve for y, you're going to get y equals 2 plus, again, you would get, oh, this would have been a negative 2 thirds. Minus 2 thirds x. If you solve both equations for y, you'll realize that they are parallel, which means that they are never crossing, which is why there's no solution. That's the two special cases. So I've kind of summarized it with this table. Most of the time when you are solving a system of equations, there's only one solution. It means they cross just once. Algebraically, it means your point that they're going to cross is going to be, x equals a number, y equals a number. If there's no solutions, it means they never cross. It means they're parallel. Algebraically, you get a statement like 0 equals 2. That's false. Infinite solutions means that they're the same line. They are always crossing. Algebraically, your variables go away. You get a statement like 2 equals 2. Here's what it looks like graphically. One solution, two lines, different slopes. They cross just once. No solution, the lines are parallel. They are never crossing. Infinite solution, it looks like just one line, but it's really two. They're just stacked on top of each other. So they're infinite solution. They're the exact same line. Last part we need to do is just an application. I mentioned this at the very beginning that businesses use systems of equations to find what's called the break-even point. We'll get to that in a second. In order to understand the break-even point, you need to understand two vocabulary terms from businesses. One of them is called the revenue function or the revenue equation. The revenue equation is how much money we bring in. Revenue is money brought in. Money brought in before we take into account the cost. The revenue equation is how much we sell each item for is equal to the number of items sold. It says it right there. Cost function is how much money we pay out. It's going to be the fixed cost, that's all like the overhead and the rent and all those types of things, utilities, plus how much it costs us to make each unit times our number of units. The break-even point is when revenue is equal to cost. It actually means we're making no money. The profit equation is when we take revenue and subtract out our costs. Profit is how much money that we bring in after we take into account our costs. The break-even point would be also when the profit equation is equal to 0. Because if revenue is equal to cost, revenue minus cost is going to be 0. So there's two ways of saying the break-even point. It's revenue equals cost or when the profit is equal to 0. So we're going to try an example question of that. So let's say a company makes bikes, has a fixed cost of $100,000. That's all the startup and the overhead and things like that. Costs them $100 to make each bike, and then they sell them for $350. Find the break-even point. So first we should define our variable. X is equal to the number of bikes. Break-even is when revenue is equal to cost. Revenue is how much money that we make. We sell them for $350, so $350 for each bike. The cost is $100,000 plus it costs us $100 to make each bike. If I subtract $100 off, for each bike we sell, we're really bringing in $250. And now I need to take 100,000 divided by 250. And in order for the company to break even, I take 100,000 and divide it by 250. And they would have to produce and sell 400 bikes. That's what the break-even point would be. Last part, define our profit function and estimate their profit if they sell on average 3 bikes per workday for 2 years. So the profit is revenue minus cost. The revenue is $350 for each bike minus, now you need to put parentheses because the cost has multiple parts, plus 250x. So you need to distribute that negative through. You'll then get 350x minus 100,000 minus 250x. Oh, sorry, 100. I don't know why I keep making mistakes today. 100 is how much it costs to produce each bike. I was doing the first step in my head. 100 minus 100. That means they bring in $250 for each bike minus the 100,000. So this is their profit function. Now the question is, what would their profit be if they sell 3 bikes per workday for 2 years? To estimate workday, we're not going to take into account holidays, so this will be a little bit of an overestimate, but that's okay. We know that there's 5 workdays every single week, and there's 52 weeks in a year, and then we'll do 2 years. So 5 times 52 times 2 would be 520 work days. And they said that they sold 3 bikes for every workday. So if I take that and times by 3, that'd be 1,560 bikes. It's a little bit of an overestimate, so maybe they would round down to do like, I don't know, maybe 1,250 or something to be conservative. So then if we put 1,560 bikes in there, 250 times 1,560 minus 100,000. Should write this as over 2 years. $250 times 1,560 minus the 100,000 would be $290,000 over 2 years, just for selling 3 bikes every workday. And that is it. So that's the beginning of the sections on solving systems of equations. Thank you very much and have a good day.